Swayam Prabha. Digital India. Educated India.
I'm now going to talk about going back to the topic we started with, which is that we want to minimize optimization of a function over a open set. Okay, so we are going to talk of minimizing a function f over a set x, so over a set S subject to S, x and S. So my feasible region S, this is my feasible region, and this is some open set. Okay, and I'm going to assume that f is differentiable. So let me write the theorem. Let x star in S be an optimal solution of the optimization problem. Minimize the function f subject to x in S. Let f be differentiable and let S set of Rn be open. Then we must have this. If you look at the derivative of f at with respect to x evaluated at x star, then this derivative must be equal to 0. Okay. That is the conclusion. Okay. Let me make sure you understand what this theorem is saying. It's saying that consider this sort of optimization problem and suppose there is an optimal solution. It is not saying there is an optimal solution. It is saying suppose there is an optimal solution. And the optimization problem has the properties that f is differentiable and the feasible region is an open set. Then it has to be that the derivative of the function with respect to x evaluated at x star is equal to 0, right? Okay. So now let's just prove this. Okay. Since x star lies in S and S is open, what do we know? If x star is a point in S and the set S is open, then what must be the case? Then there is a ball around x star that lies completely in S, right? So the picture you should have in mind is, so suppose imagine this is your set S, this is your point x star, and there is a ball around it like this that lies completely in S. Okay. What that means is, so there exists a radius r greater than 0 such that x belongs to S whenever the distance between x and x star is less than r, right? Okay. Now, what is unique about the ball? What is so interesting about, okay, there is a ball around the point x star which lies completely in S. So what? So what if there is a ball around? So what's so great about the ball? So, there are many interesting things about the ball, but the thing that that is of relevance here is that, remember, the unit, any ball, okay, of unit ball or any ball of any radius, positive radius, is essentially like all of Rn shrunk down to a smaller radius. So, what that means is, if you look at x star and you look at any other point in Rn, okay, look at the direction starting from x star going towards that other point. Okay, let us call that other point y. Look at this direction that starts from x star going towards y. That direction, okay, this is a ray that starts from x star, goes towards y. What I can do is, without changing the direction, I can simply shrink this ray all the way down to the point where now that ray is present completely in the ball, right. So, any direction I can conceive of which is present in starting from x star towards which I can go in Rn, all of those directions are also present inside the ball itself. Okay, it starts from x star towards some point in the ball, right. So, what that means is, so for every vector h in Rn, okay, I can find some eta positive, okay, such that if I look at the vector x plus delta h, okay, now I will tell you what delta is. This vector x plus delta h belongs to S for all delta that are greater than equal to 0 and less than equal to eta. So, take any direction h, okay, right, take any direction h, and what I can do is take that direction and scale it down by multiplying it with a factor delta, such that now x plus delta times that direction lies in the ball. All right. So, this lies in the ball and therefore in S. Is it clear? Okay. So, for every vector h, there exists an eta such that one can do this. Okay. Now, since we know that x star is optimal, is an optimal solution. So, what does that mean? That means that f of x star is less than equal to f of x for all x in S. Okay. But then I can in particular take a point like this, take a point like x star plus delta h, which is also lies in S. In particular, f of x star is less than equal to f of x star plus delta h. Whenever okay, and now remember that delta can be is the way you shrink, what is the factor by which you have shrunk the vector h. Okay. So, now we are going to make delta smaller and smaller. So, if delta is smaller and smaller, then x star plus delta h is very close to x star itself, and then we are in the regime of Taylor's theorem. Okay. So, now what does Taylor's theorem tell you? Taylor's theorem implies that f of x, Taylor's theorem tells you that f of x star plus delta h is equal to f of x star plus this thing, this derivative of f at with respect to x evaluated at x star times now x star minus x star plus delta h minus x star. So, that is just delta h plus something that was going to 0. Okay. Now, go back to what kind of factor it was. It was going, so Taylor's theorem said that there was, okay, my slightly bad choice of notation, because here there is this, I have used h for the function, but I hope you will still be able to get this. This factor here, which was going to 0, it is such that h itself goes to 0 as y goes to 0, y minus a also goes to 0 as y goes to 0, but because h goes to 0 as y goes to 0, what this means is this residue that is left is such that if I divide that by y minus a, that also goes to 0, right. So, another way of writing Taylor's theorem would be to say something like this, would be to say that this is equal to the f of x star plus delta h is equal to f of x star plus this derivative times delta h plus something which I will write like this, small o of delta. What do you mean by small o of delta? Small o of delta is just a generic notation. It stands for the following. Small o of delta is just is any quantity such that any quantity, say theta of any quantity theta of delta, such that if I look at any quantity, say theta of delta, such that if I look at the limit small theta of delta divided by delta, this goes to 0 as delta goes to 0. Okay. So, its small o of delta means that it not only does it itself go to 0, even after dividing by delta it goes to 0, all right. So, now this is a way of writing things in optimization. We make this kind of shorthand. We don't really need to know what this exact thing is, so long as we know at what rate it goes to 0. Okay. A quantity can go to 0, but it can, so you can have a quantity that theta of delta that goes to 0, but then theta of delta divided by delta may not go to 0, right. But in this case, this is a quantity where theta of delta itself goes to 0, and upon dividing by delta also it is going to 0. Okay. So, that is the significance of this. So, what Taylor's theorem is basically telling us is that f of x star plus delta h is equal to f of x star plus this derivative times delta h plus this quantity, which means this is something such that small o of delta divided by delta goes to 0 as delta goes to 0. Okay. All right. So, since that is the case, now what we get is, so now f of x star is we know that f of x star is less than equal to f of x star plus delta h. So, consequently, we get that so if I look at this difference, f of x star plus delta h minus f of x star, that difference is greater than equal to 0. So, consequently, I get that this is now this holds for all delta this holds for all delta in some neighborhood 0 to eta. So, what I can do is take delta greater than 0, that allows me to divide throughout by delta. In that case, I have that this is true. Now, since this is true, I can now let delta go to 0, then that would give me that the derivative of f with respect to x evaluated at x star times h is greater than equal to 0. Okay. Remember, this derivative is a row vector, h is a column vector, this times this scalar is greater than equal to 0. Right. Now, I can do this. Okay. So, this is greater than equal to 0. Now, what did we want to show? If you go back to the to the claim of the theorem, it was saying that the derivative is actually equal to 0, right? But remember, now what I have got is that this inner product, the inner product that is written here, the derivative times h, this guy is greater than equal to 0 for every vector h, in Rn, right? Because I started off with h as an arbitrary vector and I got that this thing should be greater than equal to 0. So, since this has to be greater than equal to 0 for every vector h, okay, what does that mean? Yeah. So, this must also be true for minus h, right? Or it must be true in particular if I take h to be this negative of this derivative itself, right. So, I can take for instance h to be the negative gradient of f, and so that would then give me that my negative of this derivative evaluated at x star, the norm of the whole thing squared should be greater than equal to 0. With that, so now the negative of the norm squared is greater than equal to 0. That just means that the norm of this derivative, the squared, is less than equal to 0, but it can't be strictly less than 0, which means it has to be equal to 0. But when the norm is equal to 0 means the vector itself is equal to 0. So, okay. Okay. So, that proves the theorem. Hence proved. Okay. So, now let us understand the consequences of this and also understand what the limitations are. So, the main consequence is, remember that when you are searching for a minimum of a function over an open set, there are infinitely many possible options there, infinitely many possible choices. What this is saying is, what this theorem is saying is that, well, if you wanted to look, instead of looking over all of them, you can actually limit yourself to searching over those points for which the derivative is equal to 0. Why does it say that? It is saying that because this is a necessary condition. Any minimum must satisfy this, right? So, searching over the full space, full feasible region, has been reduced to searching over solutions of this equation. Solutions means solutions x star of this equation, right. Now, what kind of equations are these? How many variables and how many equations? X star itself was in Rn, and this is the derivative of f with respect to x, right. So, there are n equations, n variables. Now, usually the difficulty arises that these equations are not necessarily linear. So, you need some numerical methods to find the solution, but it is still better than having to search in the entire space with, right. So, this is how optimization works. You first try to find a mathematical result which constrains your search, and then you come up with an algorithm to go and search in that particular region. Okay. So, this is otherwise there is you would without a result you would be searching everywhere, and that is too expensive. Okay. All right. So, I want to also tell you this is one consequence, but also some cautionary remarks. Okay. Now, remember what we said. Remember, the theorem said that if there is a solution, then this must hold. Okay. So, there are many different cases and sub cases that arise because of this kind of statement. So, let us go through all of them. The first case, so let me try and the first case is, so let me write it this way, existence of solution of optimal solution. Second thing is number of solutions to this equation. Okay. And then you have consequences. Okay. So, let us take this case by case. So, suppose there is an optimal solution. Okay. Now, if there is an optimal solution, then we know that it must satisfy that its derivative is equal to 0. Okay. If there exists an optimal solution, this must be true. Okay. And now, suppose there is only one solution to this bunch of equations. So, there are these nonlinear equations. Okay. We know that these nonlinear equations must be satisfied by the optimal solution, but there may also be other points that solve these nonlinear equations, right. But suppose there is only one solution to these nonlinear equations. Okay. So, suppose only one solution, then what does that mean? That has to be the optimal solution, right. So, every optimal solution must satisfy these set of equations, but then these set of equations have only one solution. Then it has to be that solution is the optimal. Okay. So, then the x star that solves these set of equations is the unique optimal solution. Now, suppose there is a solution to this set of equations, to the optimization problem. There is an optimal solution, but when you look at these nonlinear equations, okay, you will find more than one point satisfying it. So, more than one point solve this, more than one point x star solve this. Now, if there are more than one point that solves this, what does that mean? It doesn't mean anything. Any of those any of those could be optimal solution, right? Okay. No particular conclusion that can be drawn. Okay. Now, suppose there is no optimal solution. Suppose there is no optimal solution and no solution here also. Then of course, then again nothing can be said. Suppose there is, again going further, suppose there is no optimal solution, okay, but there is a unique point at which you can solve this system of equations. What can one conclude about this? Again, we can't say anything. See, remember, because the theorem started with the premise that you have a solution. If there is no solution, the theorem will not tell you anything. Okay. And again, once again, suppose there is no optimal solution, and then there is more than one solution to this. That also does not say. I will, yeah, one second. I will let me illustrate this for you through some examples. So let's do the first case first. The first case is when there is an optimal solution and there is a unique solution. Okay. So what I'll do is I will take S to be say -1 to 1, the open interval -1 to 1. All right, and let's draw some functions illustrating this case. Here is -1, here is 1. Okay. So I'm minimizing this. There is a, and I find that there is a unique point here like this, where the derivative has become equal to 0. Okay. Then it has to be that this is also the optimal solution. So this is the happy case. The second case is, once again I am on -1 to 1 like this, and I have a function that looks like this. So now if you look at the derivative of this function, the derivative of the function has become 0 here, and it's also become 0 here. So there is now more than one point where the derivative has vanished. Okay. So we need to dig deeper in order to conclude what the optimal solution is. So in this case, we have to dig deeper. That's a separate matter. The theorem does not help us conclude anything further about this. Okay. What does case 3 look like? No optimal solution and no derivative also does not vanish. So just take for example, we are taking I want to keep the domain as -1 to 1. So I just take say just a line like this, right? So there is no optimal solution. The infimum is not attained in this set. It would have been attained at -1 if -1 was part of the domain, but it's not, right? So the domain is open. So the infimum is not attained, and also the function shape is such that its derivative does not vanish anywhere here. Okay. Let's look at 4. So 4 is actually a case that's very tricky, because so here you have a unique solution to the equation that derivative is equal to 0, but there is no guarantee that the optimal solution actually does not exist. So what does that look like? Yeah. So just invert this figure 1. If I invert this figure 1, just see, for example, you do this, look at this sort of figure. There is no the infimum is not attained in this case, but there is this point here where the derivative has vanished. Okay. So, this is case 4 is often responsible for many errors, because before checking that a solution exists, people jump into checking for solutions of derivative equal to 0, and then often come up with answers that are not actually solutions of the optimal solutions of the problem. Okay. And then question 5 would look say something like this. Again talking of -1 to 1. Again, there are now multiple points where the derivative is vanishing, right? But there is no solution. Let me draw this even further down. Yeah, this is, yeah, solution does not exist.